Hello and welcome to the continuation of the dimensional analysis lectures with part 2 of that PD example. So let's see where we were. Okay, so what did we do? Oop, I'm flipping all these pages. So flip, flip. All right, so we're looking at this diffusion equation, the heat equation, right? It's up here. And then we assume that there is a relationship between all the physical quantities that are appearing in this equation, right? It's not only the space x, right, and the time, but also an initial velocity. So I don't want to go over everything in detail. The point is that there is a relationship between all these quantities that has to mount to a non-dimensional quantity on the right-hand side. This means that whatever physical dimensions these physical objects have, right, when we put them together in terms of the fundamental units, which in this case would be mass, right? So we have mass, length, and time. Okay, so when we put them together, we mount, the powers of these things should end up to 0. So then we figure out what are the dimensions of everything, including this d, which was the diffusion coefficient, right? So, and then we ended up with a linear system, right? Here it is. And then we did a little bit of linear algebra to solve this system, which has not necessarily a unique solution, because, we're above that level, right? And we did a little bit of remembering of linear algebra. The point is that looking at the matrix, the matrix expression of this linear system, we have A, the matrix of the coefficients, just looking at the rank of A and the number of equations and the number of unknowns, or if you want equivalently, the number of rows and columns, we can figure out how many solutions we're gonna have, right? So long story short, we ended up for this system with a solution that has two independent variables. In other words, two of the unknowns are free to be whatever they want, okay? Whereas the other three, so here we had 5 unknowns, right? So 5 is the number of unknowns, right? A, B, C, D unknowns, right? And then these two C and E, right? These two unknowns are independent variables, and the other 3 can be expressed in terms of these other 2. And now we did the linear algebra. We go back to, so why are we doing this? Okay. And why are we doing this is because now when we're going to the original problem, when substituted into the dimensional expression of the original modeling of the equation, right? So the original was like f of x, t, d, u naught equals 0, this functional relation in between the physical quantities, right? So when we substitute their a, b, c, d, e into their dimensional consequence, right? This quantity that we obtain here has no dimensions, right? So now we have some freedom there, right? Because C and E, remember C and E, right? Where are they? They're up here, right? So C and E are free to be whatever. So we can choose them to be 1, 0, 1, 5, whatever. Any choice is good, right? So now the question is, how many dimensionless quantities we're obtaining that are independent of each other when we substitute C and E, okay? So yeah, we're obtaining for a choice of C and E a dimensionless quantity, right? Now I'm gonna choose another one let's say I'm choosing now C is 0 and E is 1, right? So now if I'm substituting in there, I'm going to get that. So I'm substituting this into up top here if you want, right? So we're going to end up with X at power, so what is C0, right? So X at 0, right? Then what is this? T would be at B, which in this case is again 0, right? And then D at power C, which is 0. And then U at power D, which is, okay, -1, right? Because E is 1, and then it's multiplied by -1 here, right? So this is the D row if you want, right? And then U naught at power 1. So then we have this U minus 1, U naught at 1, that again is dimensionless. Okay. So in other words, for every choice of C and E, we compute A, B, and D, and then we're going to get a dimensionless quantity, right? So the question is, how many independent dimensionless quantities do we get like this? And the answer is like the linear algebra. Well, how many independent vectors do we have there, right? In the right-hand side, you know, this C and D. Oh, about 2. Huh? So there you go. So in other words, it coincides with the dimension of the space of solutions of this linear system. So there you go. Let's see. Okay, so I'm going to write now what I was telling you here in words, kind of, right? So, for every choice of C and E as real numbers, right? We get A to B. So I'm going to just pick it up from the other side. So this was my minus 2C and nothing. B to B, I'm sorry, I'm flipping, but that's the way it is, C. And then D to be given by minus E, okay? Or if you want, for every choice of C and E, and, let's do this, sorry, and, okay, we get X at A, T at B, D at C, U at D, and U naught at E, right? To be a dimension, or if you want, dimensionless. Okay, all right. So it's a dimensionless quantity, okay? So in other words, not dimension, sorry. So it's not dimensionless. To have, that's stupid of me, okay, not to be dimensionless, sorry, okay. So this one to be 1 actually, and now it comes X at A, T at B, D at C, U at D, and U naught at E. So this is a dimensionless quantity. Okay. So what did I write here? I didn't write that correctly. Ooh, okay. So it's not dimensionless, this one, right? It's like, it's 1, right? Because it's given by mass at 0, L at 0, time at 0, right? So that's what I meant. Okay. but this is correct. So this is a dimensionless quantity. So now comes that question, how many distinct dimensionless quantities do we have? How many distinct dimensionless quantities are there? Okay, so that's the word, the key word, distinct. Okay, so well, for example, right, we took C's 1 and E equals 0, and then we ended up with x at minus 2, right? So what was here? Okay, x at minus 2, t at 1, d at 1. So this is dimensionless, and let's call it pi 1, okay? So we also took C0 and E is 1, and we ended up with the other one, U at minus 1, U naught, that has no dimension, and let's call it pi 2, okay? So for every C and E choices, I get a different one. So the question I ask here is how many distinct are there? And the answer is how, you know, it's, we're gonna have as many as the dimension of the span of solution of the linear system that we just solved. So basically we can say something like, look, for this example, okay, we have two distinct solutions, okay, and the rest, so two distinct solutions, the one that we have for C is 1 and E is 0, and then C is 0 and E is 1, let's say, and then the rest or any other solution, any, let's say like this, okay, any other solution A, B, C, D, E that makes this A, X at E, B, what was this one, D, right? That makes this thing dimensionless can be expressed in terms of, okay, this I don't know how should, okay, main ones, okay, main ones meaning these guys, okay, all right, there you go. So in other words, if I take any other solution of the system, is basically, so note, this is linear algebra, right? This is because the span, okay, I should put it like we said, the solution X equals A, B, C, D, E, right? We wrote this one last time, is actually written as C, and then, not the solution, solutions, right? And then we have minus 2, those vectors there, where are they? There you go, minus 2, 1, 1, 0, 0, plus E, 0, 0, 0, minus 1, minus 1, right? So any solution X is like this, right? So if we call this one V1 and this one V2, right? The dimension, right? The solution is actually X, right? Belongs to the span of this V1 and V2, and it's basically the space of solutions is two-dimensional, right? The space of solutions is two-dimensional, right? Oh, we're going to confound it with the other dimension. Okay, yes. 2D. No. I'm trying to not confound it with the dimensions of the physics, right? So that's a different story. Okay, so this being said, before moving on, I want to go back and see, you know, like, okay, I'm trying to do the theory of this. So what the heck are we doing here, right? We have a phenomenon that we model using a certain law, okay? So there you go. But in this law, each letter, if you want, so in this law is described by a combination of physical objects, right? And these objects, right, have a dimension. Now, when we combine them, right, you know, so I'm combining the space with time, with diffusion coefficient, with velocity, right? When I combine them, right, the result should be, I'm asking for the result to have no dimensions. I could ask for the result to have a dimension, but which one should I choose then, right? So what about if I choose length? But why are you choosing length? Okay, so I'm starting with the premise that the physics of my problem that combines all these physical objects, right, that they have dimensions, all of them, when I combine them, right, I combine their dimensions, what I'm getting here, I should get something that is has no dimensions, okay? And then what I'm doing, I'm putting them together, right? They appear different powers. I don't know what the powers could be, x at 2, time at -3, whatever, right? The point is that when I'm doing their dimensions, that's why I have these squares here, because I'm thinking about their dimensions. When I'm doing this thing, right, I'm going to look for those powers in their dimensional description that when I put them together, I get something that has no dimension. So in other words, I'm going to go and express this T, D, D, U, whatever what we did here, because that's exactly what we did here, right? You see them? That's for dx, that's for the time, that's for the diffusion coefficient, that's for the velocity, that's for the other velocity, right? So I'm expressing them in terms of fundamental units. I am collecting the powers that they show up at, right? And then I'm saying, oh, all these powers, they have to be 0. Okay, so I end up with a linear system. Now, any solution of this linear system will make this combination here, up here, to have, you know, the powers of the fundamental units to show up at power 0. And thus, the initial law that I started with, this one, X, T, D, U, you know, the one that I didn't know, and I don't know what it is, right? But all I know is that now these guys all together, you know, when I combine them, I will get here something that has no dimensions. Okay. And you're going to say, so what? Okay, let's write it and see. So what? So what? I don't want to lose the philosophy. Why are we doing what we're doing? That's why I'm going back like this. It's better just, you know, to kind of. Okay, so once again, here is the phenomenon that we're referring to. Okay. What we wanted, we want this to have no dimensions. These guys are coming with various dimensions. In a way, I'm writing again that I wrote before, but it's okay. I don't mind. Okay. So once I'm doing this, what I want to get in terms of fundamental dimensions is for these fundamental dimensions to be a dimensional the combination, right? So that's why I said on the previous page that actually this is equals 1, right? Because any number at power 0 is 1, okay? But I prefer to write it in this way because it's clear what I'm doing. So now when I'm expressing these guys, all of them, right? I'm going to express them in terms of the fundamental dimensions, which are mass, those one, length, and t, right? I end up with a linear system. Okay, I should change the color. No point to keep it in red. Okay, so I end up with a linear system in A, B, C, D, and E. And then any solution of this linear system makes true, let's put 2 stars. This relation, this is the relation 2 stars. Okay, so when I substitute there the solution, I'll get that those x at A, right? The dimensions of x at A times the dimension of t at B times the dimension of d at C times the dimension of u at D times the dimension of u naught at E, right? All of them together will end up with 1. But this is just about the dimensions. Okay, so now let's say we have such a thing. We have, let A, B, C, D, E be a solution, right? Then, okay, if you want, I can put hats on it. You know, I could put like a hat or something, but then I'm complicating the notation, okay? So I'm not sure if you're comfortable just to say, let consider a solution, right? So we actually did it, right? We said, okay, so I don't want to say, oh, C and E can be anything, you know, go back. So let's be a solution, fine. Then what? Then this is true, 2 star is true, right? Fine. So what? So then this is true. This is becoming true. This f of whatever is becomes non-dimensional. Oh, okay, so when I'm combining these guys, so from let's call this one. I'm going to call it relation clubs. I don't know why. So from clubs, okay, combined with this being a solution that does the job, okay, we're going to end up that x at A, t at B, but that is that solution, not any A, B, and C. It's a solution. It's like these guys here with C is 1 and E is 0, okay? D at C, U at D, U naught at E will become dimensionless. So we'll have no dimensions here. I'll write no dimensions. Dimensions. Okay, all right. So now, of course, you know, I will have many combinations. If the linear system has more than one solution, I will have many combinations. As many solutions I have in the system, as many combinations I'll have here that have no dimensions. So the question is, how many are there? They're independent. Oh, there will be as many independent, as many solutions I have independent in the linear system. And that's where linear algebra kicks in. That's what's going on, right? So for the example we had before, how many linearly independent solutions we had here, right? The space of solutions, right, which is spanned by 2 linearly independent vectors, will have 2. So only 2 of them will be distinct, whereas the rest of them will be combinations of the other guys. That's the meaning of you know, the dimension of a linear space, right? You know, so I can choose 2 vectors that are distinct, you know, a set of vectors that are, you know, linear independent and maximal within that, you know, if you remember linear algebra. The point is that in this example, there are 2 that are distinct, and the rest of them can be arrangements of these 2, right? So combinations, linear combinations of these 2, okay? So now you're going to say, so what is this important? So for this example, you're going to have, you know, two distinct linear combinations that are there. Yeah, we're going to continue that example in a second, but not before stating the wonderful, the Buckingham Pi theorem, okay? It's not the Buckingham Palace. Actually, if we Google it, it was a Buckingham. I should Google it. It's a Buckingham mathematician, right? Actually, it should be an applied mathematician. Buckingham. Let's do that. Buckingham pi theorem. I'm going to say why pi. I don't know. Here, the Buckingham pi theorem. Here, I'm going to move the share on my screen. Okay, see, it exists. It exists. Is there a Buckingham pi theorem? Okay. In engineering, applied math, and physics, the Buckingham pi is a key theorem in dimensional analysis. Okay, I won't read all the wiki page about it. I was just saying who? Edgar Buckingham, an American physicist. There you go. Although, check it out. Although named for Edgar Buckingham, the pi theorem was first proved by the French mathematician Joseph Bertrand. There you go. It's all well. It's often that we learn these theorems by X and Y, and actually they're discovered or anyhow put down by Z and W, right? So there you go. Okay, I will let you read this page in peace whenever you want and have time, if you want to. Okay, I'm going to go back to the Buckingham pi theorem. So you're going to say why pi is because these dimensionless quantities that we're forming on the, see here, these guys that have no dimensions, right? Traditionally, they're called pies. They're the pies. Because you can have more than one, right? So it's, let's say pi, call it pi. So in the previous, we could say in the previous example, we had two distinct dimensionless quantities. Okay, let's call them pi 1 and pi 2. Following the tradition, we could call them D1 and D2. We could call them F1, F2. Call them pi 1 and 2, pi 2 to respect tradition. Okay, and we're going to go back to the example, but first I want to state this theorem so you see it, okay, in its full splendor. So we have n fundamental in a physical phenomenon that we're describing using, you know, some physics law, right? In principle, we would have some fundamental dimensions, which were like, you know, in the examples that we did was time, was length, was mass, right? Those are, you know, we played only with these three ones actually, you know, so these are, but could be more, okay? And then we have M physical quantities like the diffusion coefficient, velocity, energy, that kind of stuff, right? So what we're doing, we're then putting them together, we multiply them, right? Each one with its own fundamental dimensions descriptions, right? So this is like, well, we had X to be L, and then we have the diffusion coefficient. I forgot what was that. So where is it? I'll look somewhere else to not flip your thing. So the diffusion coefficient was ML at -3, right? So we had the diffusion coefficient to be L, where is it? Sorry. L at 2t and -1, right? So I just want to L at 2, t at -1, yeah? Okay, and it's stuff like that. So this is, you know, like put together in this Q thingies, right? So here, so this could be like X, like T, like D, whatever, okay? And then we multiply them all beautifully, and, you know, writing them in terms of the fundamental solutions. You don't have to write this because I'll give you the notes anyhow. I just want to do, this is a lot to write, so that's why I wrote it before the lecture, actually. Okay, so what we do, right? We multiply these guys exactly like how we multiplied these ones. It's the same idea, huh? Multiply, right? So instead of x, t, d, we have q1, q2, right? Express them in terms of the fundamental units, the fundamental dimensions, not units, because units is a different thing, right? We multiply them, and then we get this, you know, like mass at the power, I don't know, a plus 2b minus 3c. It's exactly the same thing, right? So that's what we did. This is what is written here, right? So we did q1 to qm, and then we do this multiplication, right, in terms of the fundamental units. And then we end up with that linear system. So you can study this theoretical setup by yourself, you know, and do it on the, match it to the example 1 and 1. The point is that we end up with a linear system. We do the linear algebra on it. Here is A, the matrix of this system, right? That we discussed the rank and whatever. I denote it by P, the powers that we're looking for, that when we're multiplying these guys, we get L at 0, L1 at 0, L2 at 0, like M at 0, L at 0, that kind of thing. So we're looking, the unknown is this one, right? These are the powers that will do the job. And then, okay, by linear algebra, we know how many independent p's we're gonna get. So these independent ones are exactly like C and E, right? In the example, we had C and E are independent. They could have been anything, right? And K, in the example, we had to be A, B, and D, which are expressed in terms of C and D, right? Dependent ones, right? So we a priori would know how many dependent and independent there are. I also bothered to give you an example here how it's done, but okay, so it's like here is a system. Here is the matrix that gives you the rank. So the rank is 2, but you have 4 equations with 3 unknowns. So just, you know, counting how many rows and columns and unknowns and equations you have, you can figure out how many independent p's you're going to get. But just looking at it, right? So this equation and this equation and this equation, they're the same. There's no information from one to another. One is obtained from another multiplied by a number, huh? Whereas only this guy is independent, and let's say the first one. So that's what I did. I took the first one and the third one, and then obviously you have 2 equations with 3 unknowns. One just goes over and becomes free to be what it wants to be. Here it is, and the other 2 are expressed in terms of, right? So for this system in P1, P2, P3, right, you have the rank of the A matrix would be 2. And then when you do, you know, how many columns you actually have 3. And then, you know, you're going to find out that you have 1 independent P. In this thing, you know, obviously I picked it to be P3. I could have picked it to be P1, but it was just easy, yeah? Okay, so coming back to the pi theorem. So we have this horrible, large linear system that we know how to solve. We know how many independent p's are. And that's the thing. When we implement any solution of that linear system into the original guy, right, we know that we will get something that is at power 0 in terms of fundamental dimensions. But basically what we're saying that this equation that describes the phenomenon that we don't know, with the choices of the solutions of the linear system leads to non-dimensional quantities that when combined, right, describe our phenomenon. So now the question is how many non-dimensional quantities we have in the business. It's how many linearly independent solutions we have in the system. So there you go. That's where this theorem is coming that says the following, right? The unit-free physical law, this one, okay? So if this one is unit-free, in other words, okay? So when we say unit-free, what they refer to this is like, it doesn't really matter if you express the units in meters or miles, right? It was that consistency business that I mentioned in the first lecture. So that's what it means, the unit-free. So a consistent unit-wise physical law, okay, is equivalent to an expression of the form f of pi 1 pi mk, where these pi 1 to pi mk are the dimensionless variables that, if you want, are solutions of that linear system that we set up with this q1 to qm. Complicated, huh? You have to digest it yourself a little bit, because actually it's not hard. So with this being said, okay, I will let you to digest it yourself. I will go back to our example and actually finish it, okay? So once again, why we're doing this? Well, the first answer why we're doing this dimensional analysis is that because when we're describing something, a physical phenomenon with these objects, right, that we have around, we measure, what happens, with different objects, right? Measure the time, measure, first of all, you describe it with this fundamental physical entities, let's just call it like this, right? And each one has a dimension, right? And then, what we want an agreement in between the stuff, because then, if you just mix and match, as I was saying, apple with goats, it's what doesn't make any sense, right? You lose the consistency in the model. So what you want to do, you want to produce something that is consistent from a dimension point of view. So especially when you have, stuff that is mixed and matched, time and I don't know, energy and forces, and the result, should not depend on what you put there, right? So, and how you measure those, in what units you measure those. So that's when one starts to do this dimensional analysis before anything. And then the results that you get are sometimes surprising, as I was telling you in the first example. Now, for this second example, we didn't finish it, but I made a kind of they took a side road to tell you about this theorem that tells you, well, whenever you're doing this job, you're going to get so many dimensionless variables that are relevant in your story. You won't get more than those. Okay, so for our example, that's where I have to go back and discuss our example further, right? So we stopped somewhere here, right? So what we did, we took the law, we found the dimensions that make it dimensionless. We discussed how many distinct dimensionless quantity are there. And we know that there are just two, right? And we're just two because that's the dimension of the solutions of the linear space that coincides with the space of solutions of the linear system that we had to solve. Okay, it's a mouthful of stuff, but that's what it is, right? So now I'm gonna go back to the problem and see, so what? It is that question, so what? Okay, so you have two. So what you gonna do now? You know. So let's see what we're gonna do now. Okay, and that's what I want to do, right? So guys, I'm not sure if how much you're following me. You can ask questions in the chat, because I know that the theoretical part might be kind of complicated, but you know, it kind of puts together the stuff, you know, like, okay, so all right, I have this many physical objects, this many fundamental units, I solve the problem, and then I get at the end that I can express it in terms of this many dimensionless quantities. That's what it says there. That's what it is. Okay. So let's come back to this. So we had this. Okay. I'm not lazy to write, so I'm going to write all this stuff again in a way. U naught equals 0. And well, for this example, we actually did know the equation, but we didn't know or do not know the solution of the equation, right? So there you go. I'm writing it here. Okay. So that's what we had from last time. Okay. So t is positive and x is in between this, right? And I was telling you that this is actually like Black Scholes of financial mathematics. Oh my goodness, we're all bankers now, okay? In disguise. Huh? Okay, so put all stuff together. Okay, we ask it to be dimensionless, so we end up, okay, dimensionless, okay, for A, B, C. I'm not lazy to write. Okay, still okay. So it was C. I'm sorry, I'm repeating myself, but if I'm gonna continue to believe in what the Latin, you know, the Romans said, repetitium mater studiorum est. Meaning repeating is the mother of study, something that people don't really apply anymore, especially the low grades, and there's such a waste, but don't start me on that path. Okay, so here we had the 1 and 1, but I don't know where. It was like a -1 somewhere. Okay, find it, I'll find it. Where are you? Okay, I think it was here. Okay, and that's not a D, that's an E. Correct. Okay, right? And now we have two independent dimensionless quantities. Okay, let's say, and there is a peak here that we're gonna choose, that we are choosing to be, okay, so what I'm saying by choosing is basically I'm choosing the C and the E, right? So these guys can be anything, not 0, both of them, okay? So it's in the span that, yeah, okay. So for reasons to be revealed later, okay, we're choosing to be C is -1/2 and and E is okay, so C is -1/2. Okay, no. We don't have to choose yet, okay? Okay. For C, let's say, okay, we're choosing, okay, given by, let's say we put C in R and E 0, okay? So for this choice, we're gonna get that we have X at minus 2C, T at C, and D at C. And let's call this one dimensionless quantity 1. So pi 1. And now I'm going to make C 0 and E in R. Okay, so now it's clear how come they're independent, right? Because it's either or, okay? So for this one, we get U at minus E, U naught at E, which you're going to call pi 2, okay? Actually, I'm going to put them hats on them because now I'm going to say what is C and what is E. So further, so these two guys, before moving on, these are dimensionless and independent of each other, right? I mean, you can see that, you know, they don't look alike at all. One has time. So one has length, time, and diffusion, and the other one has just velocity. And actually, you can see how, see, these both are velocities, right? And their dimensions, so it's meter per second, but this is meter per second at power E, whereas this is meter per second at 1 over power E if you want, right? So they cut each other, right? They cancel each other if you want, okay? So now further, okay, let's choose C to be minus a half, okay? And E to be minus 1. So in this case, we're gonna end up with pi 1 to be X over, right? So this is a minus 2C there, that. You don't say anything. Why don't you say something? If you see that I'm making a mistake. Okay. So it's X over root of dt. And guys, stop me if you don't follow the algebra or whatever is here, right? Or my rambling. Okay, so this is U over U naught, huh? Yeah. So these are the two dimensionless quantities that we're going to use to describe this phenomenon, okay? And by the pi theorem, we have that, so by the Buckingham pi theorem, we have that this fellow, okay, so let's call it relation hearts, okay? I'm gonna put the heart on it. So here, by the Buckingham pi theorem, relation hearts is equivalent to, okay, what does it say? Is equivalent to some relation that involves just these two guys. Oh, okay. So what? Well, I'm gonna flip the page and we'll see so what. Okay, so this guy that I put with hearts becomes this relation f in pi 1, pi 2 equals 0, right? So yeah, f of x t d u u naught equals 0 is equivalent to some f of pi 1, pi 2 equals 0, where pi 1 is x over root dt, and pi 2 is u over u naught. Okay, all right, if you say so, dear. Okay, with both these guys having no dimensions. Okay, just I put it there because it's there, right? So there are no dimensional. All right. So now from this relation, right? So from this one, okay. So how should I do it? So from this one, follow the arrow, okay? We have that, right? So if you want, this one is equivalent to, okay? I'll put the arrow two ways. So we have f of x over dt, u over u naught must be 0, right? Or we can say something like u over u naught will be a function. I should use a different letter. Huh? Let's say g of x of root of dt. Okay. So you're going to say, how come? Here, I'm going to make a little bracket. Okay. So for example, well, if you have, I don't know, 3x2 plus 5, something like 5x3 equals 3, right? What is y, right? So it's like y equals, right, root 3 of whatever is there, 3 minus 3x squared over 5, right? So that's exactly what I'm thinking. Like this would be the f, right? Whereas this is y equals g of x. See what I mean? That's why I say, so this relation with f, if we could, express it explicitly, one of a function of the other. So one as a function of the other one, right? So that's what I'm saying. So let's assume we can do this, right? So now, from now on, things are going on a very different path. So, I wanted to finish by now, actually. All right. So, something, we're going to stop here because I don't want to have these lectures more than an hour. That's more than sufficient, right? So next time, we're going to see a little miracle happening. Okay. That somehow we're going to end up with this is the solution of the ODE, of that PD we are going to obtain without knowing any PDE techniques. Okay, that's the thing. The solution, or of the initial PDE. So this is just, it's a kind of a side note to the dimensional analysis business, because this is not something that happens usually, but it was such a nice example that I couldn't help it, right? So, okay, once again, before we go home, in between quotes, okay, we go home. What was the purpose of today's lecture? Well, was to kind of go over this example in order to make sense of what is the Buckingham Pi theorem, which I'm looking to find here in the notes somewhere. Where was it? Where is it? Sorry, I have to flip. Where did I? Oh man, okay, so where okay, somewhere further down the road. There you go. Okay. So the Buckingham Pi theorem, what it tells us, it tells us that in a physical description of a phenomenon, if we're looking at the dimensions and we're trying to make sense of them and have a consistent model, we're going to discover that actually sometimes we can describe that phenomenon in terms of a lesser number of variables. So if we start with m, which could be 5, we might end up with 2 that are relevant and distinct in that problem, right? So that's where the gain is. So I repeat, not only that we are making the model to be consistent, but the gain is that we can describe that phenomenon with a lesser number of variables, and only those variables are relevant. So we didn't quite get to do some really cool examples, but next time, that's okay. We're going to finish this one with the PDE, okay, which is the sidekick, okay? But then, you know, we're going to do one or two, one an easier one, and then a more complicated one where I will try to convince you of the power of this theorem, okay? So this being said, I'm tired. There you go. Okay, I'll stop the recording. So bye-bye recording. Okay.